Good morning. I'm here to talk to you about how to use platform telemetry to improve data center efficiency. This is actually a talk by somebody in my team, Nishi, and Edmund. Unfortunately, Nishi had a personal emergency, and Edmund's COVID restrictions, he's not allowed to come into the country. So anyway, here I am covering for them. My name is Mohan Kumar. I'm a fellow at Intel, and I lead the data center cloud architecture team. And I'll cover the few topics here on, I think you've heard previous talk. Also, the team covered some portions of data center sustainability. Here, I'm going to talk about more into the platform telemetry and how we can use the telemetry stack for sustainability. So a quick overview, right? So I think you probably have seen this message multiple times in this conference. This is also wonderful to see that, last year it was a challenge to, or 2 years ago, it would have been a challenge to have this message across. And now this is universal to see this message on sustainability and carbon footprint coming through clearly. So from our viewpoint in the server land, essentially when we look at the carbon footprint, basically divided into embodied carbon, the carbon that comes from manufacture, and the carbon that comes from essentially operational, when you run it in your data center. And the embodied carbon is the smaller portion of it, as you can see from the circle on the left side. The purple bar is the embodied carbon, and the rest of the blue circle is the operational carbon. That's not to say that we're not going to go work on that problem. In fact, Intel is committed to reducing. So right now we are 83% of our energy is green. Our goal is to get to 100% green by 2030 and net neutral by 2040. That's our corporate goals right now. So we will work on that problem. It's not to say we won't. But and we are also, and given that 90% of the server is operational carbon, it's important to look at how does that break down into. And the circle on the right-hand side is kind of showing you the breakdown of what that breaks into. Essentially, the green portion of the arc is CPU. Everything else is the platform stuff. So the question is, how do you work on solving that green portion of the arc, right? So we need. There's a lot of hooks in the processor and in the platform, but do we use them effectively? That's really the question of it. So this type of watch, learn, decide, analyze, decide, and act. This type of telemetry-based solution is well known for decades, right? People use this everywhere, right? What to watch? Basically, what is your performance, right? How well is it performing? What is your energy? What's your temperature? How many errors are you having? What is your and those are the things that are traditionally watched, but in this world, we also need to care about what is your throughput and latency, because those are tied to what you would think of as your service level objectives, because you need to make the customer happy, right? One time they run the workload, it takes 10 minutes, and the next time it takes 1 hour, nobody's going to be happy with you, right? So no matter how sustainable you are at that point. So that's the key part of this. And from an analysis standpoint, we see how well the CPU or the infrastructure is being utilized. We see the hotspots. We see what the workload patterns are, and I'll come to this later with an example. And we see the interference that's happening. And we also have the ability, on the basis of what is happening in terms of errors, to be able to predict something bad's going to happen and avoid that failure, rather than just have excess capacity laying around to cover this. At the hardware level, we have lots of hooks, right? I mean, you see acronym galore over there: runtime average power limiting, hardware P states, dynamic voltage and frequency scaling, and so on, right? There's lots and lots of technologies at the underlying level, and we'll get into a couple of them and see how we can use all of this to solve a bunch of problems. We need to, if you're going to use this for sustainability, which is energy efficiency, which is the obvious one. Second is performance, right? So there are interesting places where there are islanded data centers where if you're connected, you're not on a grid, so it's a use it or lose it proposition. So, how do you manage performance in the space? It's very important, right? Because saving is not going to help you any. How do you lower the TCO, which was the topic of Sundaram and Jessica's talk earlier? And then availability essentially goes to how much buffer you're keeping, right? A lot of data centers have these buffers of servers, buffers of power, essentially laying around just in case, right, to cover the spikes and also to cover the failures, and how do you avoid them, right? That's the challenge that we need to go solve. So I promise I'm not going to walk you through every line of this, but essentially the silicon hooks and the platform level hooks are numerous, right? We have the ability to, in silicon level, we have what are called MSR, model specific registers, and then there is out-of-band access to them. So then there is what's called performance management unit called PMU, and between those two, we have a lot of ability to go change the frequency. We can figure out, and we have the ability to monitor what's happening inside your silicon at a very deep level. And we also have the ability to control power through runtime average power limiting called RAPL. And you also, at the system level, you can go look at measure the power. If you're here yesterday, I talked about that one of the problems we have is that something so fundamental like measuring power is not standardized, right? I cannot go from one platform to another to essentially say, here is my way to measure power and get that out. And this is one of the things we are working through OCP. The OCP has a redfish profile in the hardware management project. The problem is it's an optional, it's not mandatory, I should say. So one of the goals is for us to make it mandatory, then we can rely on it from platform to platform regardless of who it is. Then you can say, I'm going to go build a solution around it. So those are, and similarly we have a lot of hooks on the thermal side that we can use as well. And again, this is just to show you the capabilities that exist, and maybe just fly through this because I want to get to some of the examples here, right? Item number 1 on the picture, I don't know if this is really talking to the power management states, the performance states, right? So you can control the frequency, P1, P2, P3, basically control what kind of performance you have. The P state basically means what's the frequency, and corresponding to the frequency, your power changes, right? So you have a minimum frequency, you have a base frequency, and then of course you have the turbo frequencies. But you have control over these things, right, on what you want to do. And then you have what's called speed select. So these are not, when you're in a multi-core system, they're not common for all the cores. You can basically say, these 3 cores, I want them to turbo up to a certain level. These 3 other cores, I only want them to have a little different frequency. I can even select what is the base frequency for each one differently. So those controls, again, come into play when you want to do this type of sustainability optimizations, because if you're running it for a specific purpose, you don't have to give all the power or energy to a core that doesn't need it per se. And then lastly, when you're idle, you have the P state control, the core state controls, which are called C states, and there are a number of those C states. They are, as you go into deeper C states, you get more power savings. But of course, you pay for it with latency when you wake up from that state. So you have to balance what you want to do when you go from one state to another. The table is kind of showing what the transitions are. Yeah, the C0 is the operational state that you typically run in. And from there, you can go to C1 to any number of states that you have. C1, C2, not this, yeah, C3, C6, and so on. So don't ask me why there are certain numbers that are skipped, just the way it worked out. So there is the point of this slide is to say that there is a lot of rich capabilities, right? And they are used for idle power management. They are not used so much for sustainability oriented work. So there is, so essentially what that would look like. So the question then would be, what would that look like? What that would look like is the bottom layer would be all the hardware mechanisms I talked about, all the hardware hooks we have in the platform. The middle layer would be how do you expose it to upper layer software, which would be OS, right, which has rich power management thanks to its origins in a laptop where they have to do mobile power management. And it luckily is carried into servers. So the green portions of it has really good support, and then that gets exposed through some standard mechanism, redfish, whatever the mechanism, both in-band and out-of-band, to the upper layers. And now this is where the tie-in breaks down, right? There is no tie-in here to take this intelligence and give it to the cloud OS. So the cloud OS can say, okay, not only am I going to use it, but I'm going to use it in a way that makes sense, right? That I don't violate the workload's SLA, right? And that's where we need to go work on in some sense. So I want to take a couple of examples and walk you through them. And so what this on the left-hand side is showing, the very green portion at the very bottom is essentially on average, if you take a rack and you're running your workloads on all the servers in the rack, and you're looking at the power, the green portion represents where your power is on average when you're running. The middle portion, I don't know how it renders, it's supposed to be red, but the red portion basically is where you spike into. Whenever there is workload demand that spikes, you spike into that region. The yellow portion is there because that's actually what the provision power budget is. Because, you know, if basically it goes to what you define as thermally designed power, the vendor says, my system is 2000 watts, but is it 2000 watts? 2000 watts at, you know, you're running at peak, right? At that peak workload, if it never happens, you just have this buffer laying around that's essentially unused. So, and this is very typical, right? 15, like almost 30% of the provision power capacity is never utilized, right, on average. So if you look at it, so the question is, you know, what do we do with this power? You can really not provision for it, because if a peak does arrive, you don't want your server rack's power breaker to trip on you, right? So the only solution is to essentially have some way to tide over that period temporarily. And the solution that we have put together is this dynamic rack power provisioning. What it does is it's a group power capping policy. So we take all the servers in the rack and say, together, your power budget is X. And that budget is not exactly, let's say all the servers together are, you know, 10,000 watts. But we tell the servers, your budget is 8,000 watts. And then those excess 2,000, it's for them to manage it within there, right, with a buy. Not everyone has to throttle, but somebody has to throttle to keep everybody within that, under that limit, right? And that responsibility is given to the dynamic rack power provisioning controller. And just so you can operate in that red zone, essentially you can also put in like a battery-backed unit on a per rack basis to cover those peaks. So then you literally can provision your rack. You can improve your rack utilization because you can pack more stuff in your rack. And also, you're not wasting your power, right? The power that you put in is really actually used power, not power that essentially you're wasting. So overall data center utilization goes up, therefore your sustainability numbers go up, because if you've seen the measure of sustainability, unfortunately, even today is PUE, power utilization efficiency, which is essentially how much went to IT power versus how much didn't go. Here, what you're doing is you're improving that ratio by reducing what's power that you provision but nobody used, essentially. Okay, am I done on time? It's okay. Second, I want to so these days, everything is going to microservices. So everything that I talked about, you know, it's all very well when you have total control of the system and you're running, you know, VMs and containers and whatever. What if you're running microservices and functions? So with microservices, they have this concept of service mesh, and what you show, sorry, actually, does it work? Yeah, these things here are the service proxies. They call them sidecars. Essentially, what you do is with every service, associated with every service, you have a sidecar that's acting as a collection agent for the telemetry corresponding to that service. So you could have So this guy is just there to collect telemetry proxy. This sidecar is for these two cores that's running this service and so on, right? So, and what this allows is to allow us to collect the telemetry, and that telemetry allows us to do better sustainability. And the way that goes is as follows, right? Essentially, you figure out what is the service level tail latency you're seeing on these workloads, right? Because there is a function dispatch, the dispatch or an dispatch comes in, and you're servicing the request, and it moves on, and you have a certain latency that you're dealing with. What's tolerable is something that you're continuously measuring. And you continuously measure what is the distance between what did you agree as the service level agreement and what is the current latency that you're seeing on average. And the distance between those two is your headroom for sustainability optimization. So then you go there and go change your hardware states to reduce your frequency or voltage or whatever to essentially get, but you have to keep it so you are not hitting the danger mark, and that's what's shown at the bottom of this slide, right? So essentially, this is your latency numbers. You have to keep it above that level, below that level rather. So, yeah, below that level. So you're not running into issue. By doing this, we were able to show a 15% improvement in energy efficiency. So there is a lot that we can do by, in terms of server telemetry, by taking an approach of taking the hooks that we already have and repurposing them for sustainability as opposed to idle power management, which is all that we do today, right? And we are actually in the process of writing a white paper that we will be contributing to OCP that goes into the details of this. And there is a lot that we can do together to adopt these principles at all levels of the data center. And I think with that, I think I'm almost out of time, so I'll stop and I think maybe 2 minutes to take any questions. Thank you. Yeah.
With the telemetry samples, are you also time stamping so you know what your relative delay is from the time of sampling?
Yeah, those are all timestamped. That's right.
Thank you.
Thank you. Yes.
So you mentioned that essentially the case study you had, one of the microservices essentially doing a data collection of power. Is that, did I understand that correctly?
Yeah, on the one that two slides back.
Yeah, 2 slides back.
Yeah, it was collecting power. Yes. Yeah.
So essentially, part of every cluster, you'll have an additional service that collects
How you're using power.
how you're using
Yeah.
power, and that's distributed across all your nodes.
Right. So he's asking if you're collecting power data on this chart, and yes, we are actually, I forgot. Yeah, not only we're collecting power, we're also predicting the workload and how the workload is actually going to behave. We know when the workload comes in, it typically uses this level of power, because we don't want to wait till the workload starts ramping up and then find out that we have a power problem, and then start trying to clamp it. So we kind of predict what's happening on the workload level, and we're also measuring the power. So between the two, we're able to say, okay, we're going to keep this under a certain given power budget. Yeah, so we are able to measure the power.
Okay, thank you.
Okay, thank you. I think I'm out of time.